Okay, so our second theorem for this board, the language. I don't know if you can see it's the language E subscript DFA. It's the set of elements. The elements are of the form angular brackets A, and where A is a DFA, and the language recognized by that DFA is the empty set. Okay, so that's what this is. And the theorem statement, here's the theorem statement, usually between quotes, is that this language is decidable. It's a decidable language. And so how do we prove that? Because the theorem 4.4, chapter 4, the fourth thing in the chapter. I think it's also the fourth theorem. Okay, so how to prove it? Language is decidable. What does that mean? I've done this many times. It means there's a Turing machine that decides that language, and that means the Turing machine accepts every string in that language and rejects any other string. Right? So how to prove it? Now remember, there's no string. There's no little w. There's the string angular bracket A. Be clear. There's two different kinds of strings we're talking about. There's this string goes into the Turing machine, and it contains information about your DFA that we call A, like here. Right? It's confusing. Sipser now often. He also uses A for the language, which is confusing. Anyway, so be aware of these distinctions, right? Because they can confuse. Anyway, so you're going to check, yes or no, whether there's an algorithm that shows whether there is a DFA, call it A, yeah, whose the language that DFA A generates is the empty string. Test for that. Well, so you input the information about the DFA. So from that you know all the transition rules, right? The formal definition of that automaton. It's a DFA. So that would be a 5-tuple, including the transition function. Right? So now the Turing machine, T, it knows all the transition rules of this machine A. Okay? So it can behave like this machine. Now, so how could this machine, Turing machine T here, how could it know whether this machine here always rejects? So if some string goes into here, that this machine here, A, will always reject, right? Because it's always rejecting. It's the language that it recognizes is the empty string, right? It doesn't accept any string. Right? So how do you know that a machine is rejecting every string? Well, that translates, if you think about it, that means that DFA never ends up in an accept state, right? So it's always rejecting. So it never ends up in an accept state. So you can have your Turing machine T check that that's the case. So it goes looking to see if this machine A, the DFA A, to see if starting at its start state, right? Because we have that information, because we have this encoded information. We have the full formal definition, including the transition rules, the transition function. We know the start state. That's one of the 5 things in the 5 tuple of your machine A. So we know the start state. All right. Well, then this Turing machine T, it can start with the start state of A. It can look at all the transition rules and just branch down for all possible transitions, the history of them, and see if any of them end in an accept state, right? So, and you don't need to know about the input stream. Like you could check so you've got all the rules. So you just generate all possible, in a sense, derivations. That's more for grammar. But you've got the start state, and you've got all the transition rules, and so you could generate all possible next. Well, there's only one, isn't there? Well, you just keep going, right? We're talking about a DFA, right? So it's deterministic. So it's a tree. Well, it's not a tree. It's history. It's state transition history. It's just a line. It's just from one state to the next, to the next, to the next, to the next. So it's just effectively a line. Thinking real time here, because it's a DFA. So you just go checking from one state to the next. You start with the start state, which is known from here. You look at transition rules and you find what the next state is, and the next one, the next one, the next one, the next one, and so on. And each time you check whether the next one is an accept state. But why couldn't that go on infinitely? Because it's a DFA, right? It's a finite automaton. And the string, I guess that means the string length going in has to be finite. I've never really thought about that before. For a DFA, usually it means that the number of states in the machine is finite. But I've not really thought about, are there restrictions on the length of the input string for a DFA? I guess. Well, think with me in real time here. So imagine the contrary. Imagine the input string for your DFA is of infinite length. Is that possible? I need to think about that. Right. Well. Anyway, so this machine here is it's going to start with the start state. It will use the transition rules to find the next state, the next state, the next state, and each time it's checking, it'll check whether an next state is an accept state, and if it is, then it will reject. Right. Okay, so you use a kind of marking technique that we used in example 3.23. That was on page 159. So you can mark the states. So if you have n states in your DFA, you can have an extra n states where each of those states is marked. You put a little dot, like a dotting technique, right? So you're sort of dotting your states, in effect. And right, so then you go into stage 2, and stage 2 is like an outer loop, and you go through this cycle. You go through this process here, this little subroutine, if you like, multiple times, and you repeat doing this loop as many times as until you don't get any more states that get marked. And why are you marking? Okay, so the guts of the proof is here. Right. Right. So you imagine you have a